Good morning and welcome again. It's nice to see all of you here. We're especially delighted that Professor Kulkarni is here. I know we're all waiting to hear his talk, but I'll just spend a few minutes telling you a few things about him. I will never be able to do full justice. So, Professor Kulkarni is the MacArthur Professor of Astronomy and Professor of Planetary Sciences at the California Institute of Technology, or Caltech. Since 2006, he has been the director of the Caltech Optical Observatories. He's also the director of NASA Exoplanet Science Institute. Would love to hear more about that. And served as the executive officer for astronomy from 1997 to 2000. In 2007, he was awarded an A.D. White Professor at Large at Cornell University, Ithaca, New York. Professor Kulkarni obtained his undergraduate degree from the Indian Institute of Technology, Delhi, and his PhD from UC Berkeley. He served a brief period as a postdoc at UC Berkeley and Caltech before joining the faculty rank at Caltech in 1987. Professor Kulkarni's primary interests are the study of compact objects, neutron stars and gamma ray bursts, transients and variables, and the search for extrasolar planets through interferometric and adaptive techniques. He's keenly interested in developing or refining astronomical methodologies. His awards include the Alan T. Waterman Prize of the NSF, a fellowship from the David and Lucille Packard Foundation, a Presidential Young Investigator Award from the NSF, and the Helen B. Warner Award of the American Astronomical Society and the Yangtze Prize of Associated Universities, Inc. Kulkarni was elected as Fellow of the American Academy of Arts and Sciences in 1994, Fellow of the Royal Society of London 2001, and Fellow of the National Academy of Sciences 2003. We're very pleased to have him here. I can go on, but I'll stop here to invite him to share with us his passion and his area of interest. Thank you very much, sir, for coming here. Thank you.
Now, many of you think that astronomy is a very romantic science. You know, we go out, observe the stars with our eyes, and some even say astronomy is the second oldest profession in our civilization. Those are all true. It's hard to beat the kind of excitement when you go in evening sunsets to look at the stars. But I'm going to talk something might be of some interest to you, which is a long time ago when telescopes were built, they're mainly built for astronomers. So it's not something where technology drove astronomy, okay? Because astronomers wanted telescopes, so they built their telescopes. But my thesis today, and it's not a usual astronomy talk, my thesis today is that a large fraction of astronomy is driven by forces outside astronomy. That is, we're not building telescopes ourselves. We're using technology that comes from somewhere, and this has caused a huge growth in our subject, and that's what I want to talk. And then I'll give some case studies. So just to review, as a background, astronomy, we have done pretty well, actually. It's in the US certainly considered perhaps one of the most exciting physical sciences. Departments which used to be purely astronomy are now routinely a quarter of the faculty are now astronomers. So there's been a demographic shift. And you'd say, why is that? Well, it's because like some subjects, there is a golden period, and astronomy is in that golden period, which is why most of the departments are investing in their manpower and money. So if you look at what constitutes this golden period, I thought I'd just give you a broad brush summary of the last 100 years, just as background. So between 1930 and in those 4 decades, astronomers understood how stars work. It's pretty amazing. You can look at the sun, and we understand the details of how the sun works. We understand how old the sun is. We understand the future fate of the sun with some precision. Okay, so if you think about it, the amount of physical understanding, mathematical modeling of such a large object is something we actually now understand. And the growth of elements, we take for granted all the stuff we see around us. It may surprise you that when the universe began, there was only hydrogen and helium, and a very small amount of lithium. And I always say, thank God there was some lithium, because some of us need it. And okay, it's a joke. Okay, I think the mental health of people in India is a lot better than in the US then. Okay, lithium is a very fragile element. It's only destroyed, okay, and that's why it's very precious. But when the universe evolved, thanks to stars dying, you start getting more elements. That's how the universe went from not just a simple universe to a universe with elements that you and I are made of. So if stars didn't die, you wouldn't be here. Every part of most of your stuff is made up of carbon, nitrogen, oxygen, especially the iron in your blood really required a star to die, and we'll talk a bit about that. So you should be very thankful for stellar death. And we understand that. We understand how we have gone from essentially no elements to now. Okay, then ideas of neutron stars and black holes, which are essentially either very simple physical ideas or really mathematical ideas, especially in the case of black holes. They're ideas. When neutrons was discovered, they said, why can't we have stars made of neutrons? When the general theory of relativity was figured out by Einstein, there's a consequence of a singularity. But just because you have ideas doesn't mean there should be nature corresponding to that. And it turns out it is correct. We now know there's stars of neutrons, stars made of black holes. So that was a major progress to go from sort of in a sense a leap of ideas just from purely sitting around thinking and then seeing it actually exists. Cosmography and origin, I'll talk a little bit about that. 100 years ago, we didn't even understand how the universe began or whether it was ever on for a long, long time. But the most amazing thing for me, and I'll talk a little bit now, is how, in fact, from such a simple universe, we see the structure today. Okay, so let me show a picture. And what this is, and we'll play it twice, what this is on the, you see the redshift, Z is the redshift, so 0 means now, very large value of Z means in the past, so very large value of Z means the universe was very young, okay? And what are you seeing here? Okay, what you're seeing here is actually most amazing. When the universe began, as I told you, there's hydrogen, helium, and a lot of energy. Actually, there's initially only pure energy, and then some of the energy became matter. So then you had this hydrogen, helium, and photons. That's all the universe was, very simple place. And the density of photons, protons, electrons in every part of the universe was almost the same, just one part in a million different. And that's what that movie showed. Initially, it showed something which was spread all over, just one part in a million, things were different. So you'd say with one part in a million different, what will happen? You know, that's the nice thing with the universe. We have all the time in the world, okay? So that one part in a million means that if there's more gas here, it'll attract more gas. So that leads to structure. So from that uniform soup of electrons, protons, and photons, we get structure. And this is now at a high resolution. And again, it's showing from very early times to now. And this structure allows gas to condense. So pockets of gas, which is more in density, starts growing. And once you have that, you have star formation. Stars grow because there's more density. And the more stars, the galaxies. So what you're now seeing is each of these dots are galaxies. And some galaxies are, collection of stars, and you can see there's tremendous cannibalism. The universe is a very destructive place. So our own galaxy was probably formed of maybe up to 1,000 subunits of these other primordial things. Anyway, so to me this is astonishing because what I showed you is a simulation, and it's not a cartoon simulation. This is one of the most sophisticated simulations, which actually uses gravity, uses some prescription for how photons interact with matter. And you can now go and do things that is, I think, very special to science. We can actually compare our ideas, our models to observations. And in fact, we now understand the growth of galaxies, how the universe began from a uniform soup to what we see today. And somewhere in between, the stars die, and they die, which was an observation made in the 60s that the transistor density of transistors on integrated chips doubled every 18 months. That was the initial proposal by Gordon Moore. And then there's another observation by Kurzweil, who actually is a very, probably a very bright chap. Okay, a little crazy, but bright. Usually they're correlated. And he was the first, he's the inventor, he's Dragon Systems. So he was the first guy who wrote the speech-to-text software, okay. And he has some ideas about how Moore's law, in fact, is only a small part of the picture. So let's understand this, because this is very important for the talk I'm now proceeding. So let's look at data, because in this, you can always come up with ideology, but eventually data usually wins the game, because that's reality. So this is a plot which shows as a function of time from the last, roughly 30 or 40 years. And this is a transistor density. And I'm sorry you can't see some of these things here, but there's a Pentium 3, Pentium 4, Itanium 2, and for some of us, 8086, 286, and so on. That's where they are. Okay, so we can see that empirically it suggests, for reasons we fully don't grasp, for some reason in silicon, the progress is the density, the yield, the performance is doubling every 24 months. And you are big beneficiaries of this, So when you bought a camera 10 years ago, it was 540 by 600 pixels, and you paid a lot of money. And you can buy, for the same amount of money, or even less, many, many megapixels camera, because Moore's law is at work for you. Okay. Now, there's an interesting twist, because this data doesn't tell you what's going on. It's an empirical observation. Why is it 24 months? Is it something special to this technology? We don't know. Okay, and that's where Kurzweil's observation come in, and it's worth thinking through. So what Kurzweil says is, let's not focus on the particular technology. You'll ask, what is the function these transistors do? Well, at the very basic level, they're on-off switches. So it says, why don't we now go all the way from mechanical valves to vacuum tube switches to then transistors and then integrated chips. And if you do that, now you go over for the whole century and you look at the cost per unit, okay? He claims, and you'll see that this is, he has constructed this, he'll claim that in fact this curve is steepening. Now this is a log linear plot, and in a log linear plot, a constant line means it's a constant exponential or constant doubling. But if it steepens, that means the time to double is actually decreasing. So in slightly more mathematical terms, the cost is not coming down as e to the minus t, but maybe t squared. Okay, well that's pretty amazing if you think about it. So, and this no one understands. This is something a lot of people are thinking very hard about. And this whole business has such a big effect on science we do that I'll give you two examples, one in biology and one in astronomy, to show how these large forces outside their subjects are actually driving these subjects. Okay, so let me give an example first in astronomy. So here's the Palomar Observatory, and it's a beautiful place. It's located in Southern California in the mountains east of San Diego, and I'm the director of this observatory. For a long time, the 200-inch telescope was a very iconic telescope. In early October of 1929, Caltech received a check for $6 million from Rockefeller Foundation. At that time, we had a policy that if anyone gave us any donation in the form of shares, checks, whatever, we'd immediately convert it to cash. And I don't know what exactly they got, but they convert to cash. And 3 weeks later, the Great Depression began officially. So we had all this money, and no one else had the money. So that was a lot of money then. And this telescope was built during the Great Depression. And because it was such an effort, it really had a lot of symbolism, at least in the US. So for a long time, this telescope was the largest telescope. There's nothing comparable to that at all, okay? And then a smaller telescope is built about 1950 to survey the sky usually large telescopes have a very small field of view or something like that. That's a large field of view for a small telescope, large telescope. Whereas this one had a field of view which was much larger, something of that sort, roughly looking at the sky, okay? With this telescope, astronomers undertook surveys of the sky. That is, they took photographic plates, because that's what you did in the 50s until 1980s, because that was the main medium. You took photographic plates of this size, you exposed them, usually for an hour, you developed them very laboriously. Astronomers obtained something like 30,000 square degrees of the sky, which is what is accessible for the northern hemisphere. It took them 25 years to cover the sky all the way, because photographic plates are inefficient. They have a quantum efficiency of 1%. So every 100 photons that strike, only one causes a chemical reaction. Okay, and then they decide to repeat this again 20 years later, and we finished the last one. In fact, we had the last major film from Kodak, which is a very special kind. But this is a survey that was done by astronomers in the 90s. This was done with a 256 by 256 detector in the near infrared. It's not something big these days. It's really tiny. Anyway, this was all done in 5 years. The whole sky was done, north and south, in 5 years. So roughly 25 years became 5 years, and this data are better. These are all digital photographic plates here to scan and so on. So here's a great example that this is the old stuff. We used things that was available to everyone, and it was laborious. This is the new one, and this was benefited by the fact that military has a huge need for near-infrared detectors. So they invested a large amount of money, and we are the prime beneficiaries outside themselves. Okay. Okay, so I'll propose a new law of mine, and not yet immodest to say it's a law of mine in writing. And so I'm not too interested in Kurzweil sort of observations over 100 years. For me, 100 years is so long, I'm not interested actually. I'm only interested in the next 3 years, maybe 5 years. And so I want to understand, what is it that drives progress? What particular thing? Because there's no, as I told you, there's no theoretical basis for Moore's law. But I think there is a basis for this particular one, which is even if you don't have an exponential growth for whatever technology it is. My claim is that when you have two methodologies, technologies that are of similar value and they become available for the first time, then you'll get exponential growth during that period, okay? Even in the absence of Moore's law. So let me illustrate that with an opposite example. What happens? You can have Moore's law and still have no progress. Okay, so this is our DNA sequence, and so the title says it's from New York Times. It says DNA sequence caught in deluge of data. Okay, so let's understand why I would use this as an opposite example. Let's look at this. It's what I call as out of sync. So the cost of sequencing a human genome, okay, plunged, to $10,000 from 8.9 million. Okay, that's an incredible growth right there. You have to agree? Okay, that's great. That's a factor of 800 over 4 years. That's a kind of growth we'll all be very happy with. In contrast, computing has only changed by a factor of 4 over the same period. So something is going wrong here, and that's what I'm saying. Therefore, progress is not now. There's disconvergence here, and that will stop this field. So what's really happening in the field of genomics is that the machines they can now build can produce data at an incredibly high rate. But the ability to digest that in two ways is missing. One is, in fact, to ship data. This company in China, they can sequence 2,000 genomes a day. But they can't ship that data to you because it's so large amount of data, they have to, in fact, ship it by putting it on a hard disk drive and then mailing it to you, which is still the fastest way to mail large amount or send large amounts of data. But they can't also analyze this data because we're having something missing. So here's an example. You can have great growth in one thing. Unless you have convergence, you won't have the full returns. And astronomy is a huge beneficiary. And I'll show you now by an example of gamma ray bursts. Okay, so the rest of the talk is this. Hopefully you have a rough idea of what astronomy is and a rough idea of some things about technological progress. So first I'll talk of gamma ray bursts as an example of a great problem in astronomy that was unsolved for 30 years and then got solved, all in like 2 years. And that's because all things came together, in particular all the technologies for this. And then I will talk about the growth here we are having in optical wavelengths, which is back to the Morse law, and the same thing in radio. Okay, so gamma ray bursts. What are gamma ray bursts? Very interesting. If you had eyes that were sensitive to gamma rays, every day you'd see somewhere in the sky, a few times a day, you'd see a blinding flash. It'll be brighter than the brightest star. It'll be made of gamma ray. It's a gamma ray flash, and it's uniform over the sky, isotropic. That is, the chance of seeing something there or something there is exactly the same. And these were discovered in the late 60s by a US surveillance system called the Vela system. So in 1964, US and then USSR signed a treaty after which nuclear explosions could not be conducted over ground. All the nuclear explosions became underground. Because until then, most explosions were conducted over ground, okay, in air or water. And in order to verify this was in fact kept, and in particular that there would be no tests in space. Both countries installed surveillance systems which were sensitive to gamma ray bursts, because nuclear blast produces a lot of gamma rays. And they did discover great bursts of gamma rays, except they're not of terrestrial origin at all. They are of extraterrestrial origin. And for 30 years, so these were found in maybe late 60s, astronomers didn't know what this was. Here's a debate. I went in Washington, DC, and it was a room like this with 3 aisles, 3 blocks here. And some astronomers, they thought they're galactic, meaning in our own galaxy. So just to give an idea, the sun is a 4th generation star, and we are one of the 10 to the 11 stars in a galaxy which we call as the Milky Way, okay, which you can see very nicely on a nice summer night if you go out and take a look. And there are other such galaxies. There are approximately 10 to 11 galaxies, so we're not anything really special that way. So the one idea is it is in our own galaxy. It's like, and the advantage of that is if you see something bright here and you use the inverse square law or that candle experiment you may recall, then the further away the source is, then the more luminous it becomes. So putting it in our own galaxy made it advantageous, being somewhat palatable. Some astronomers thought the extragalactic, that means they're in other galaxies. Well, that makes them incredibly exotic. I mean, the amount of luminosity they produce will be so staggering. You know, it's a joke I always tell my wife that astronomers, we are used to very large numbers. You know, we'll say the sun has an energy over its lifetime of 10 to the 51 ergs, which is 1 followed by 51 zeros and then ergs. We're used to such large numbers. And even for us, a gamma ray burst in another galaxy would be mind-boggling. In practice, unfortunately, when we come home and show our paycheck, that's when we show our fondness for small numbers. Okay, and then others didn't know what they were. Someone said, well, maybe they are Klingon warships with cloaking device on. Now, only if you're a really science fiction nerd, you'll understand this particular joke. Anyway, I'm a very, you know, I may be an astronomer, but I'm not stupid, so I collected all these 3 buttons because they have great value. I have the whole collection. So some of you who are well off, you can always negotiate with me. It's one of a kind. Okay, so the debate was to figure out what it is. So there are 30 years. This is a phenomenon. It's not a trivial phenomenon. It all got sorted out in 1 year, actually. So next year, an Italian-Dutch satellite called Bepo-Sax was launched. Okay, here's a poster of that. It was a reasonably routine satellite, nothing very special technology. And yet, very quickly, when the satellite went up, we were able to, in fact, after the gamma ray burst took place, we were able to find the optical emission from the source of the gamma ray burst. We were able to use our telescopes in Hawaii. So this is 2 Keck telescopes which we manage, This is the big island of Hawaii, and this is Mauna Kea. It's the tallest mountain in that chain. But if you really count it from the bottom of the ocean, it's much higher than Mount Everest. And that's the Pacific Ocean in the distance. You may not get a sense of the idea. This is a very large island, actually. And these are the world's largest telescopes. Next is the Japanese Subaru telescope and many other telescopes around here. So some investment, just to give you an idea, on this mountaintop is probably about $1.3 billion. Okay, so this is not exactly a cheap science. Anyway, with this, we're able to show that the gamma ray bursts come from other galaxies, that indeed it is true. They're truly exotic, and we now believe that these arise from the birth of young black holes. It was so popular, this result, that I must have had about 250 newspapers, but I'll show only one, which is, it shows a purposely darkened, this is actually Bo Derek, let me put it this way, somewhat scantily clad. It's a German tabloid, and somewhere here it says, thus extreme phenomena, said Professor Kulkarni. And so here we are with Bo Derek, murder of the guard of the Pope and all that. So we really entered mainstream news at this point. Okay, so we now believe that gamma ray bursts come from spinning black holes, which can be formed in one of two ways. When you have two neutron stars that converge, they spin up, they emit jets, or if you have a large star that is spinning and as it collapses, its spin goes up and it forms. So these we believe are the birth cries of rapidly spinning black holes. Okay, so what led to this breakthrough? If you look at the detectors on Bepo-Sachs, the satellite, they've been around for years. In fact, all those detectors could have been built in the 60s and were built and were put in space. What changed was that as soon as the satellite could look at the data, we really had large format detectors. So we could take a picture of that piece of sky. We could analyze the data in real time. We could disseminate this, through internet. And we could then swing the telescopes. So the fact that we could do all this in an hour, whereas in the past, all this would take a week, changed this whole situation. Okay, so this is an example of convergence of the positive sort. The DNA sequence is a convergence waiting to happen, and there's a convergence that happened, and in 1 year, we could do 30 years of progress. Okay, so now let me get on to the next one, which is synoptic optical imaging. Synoptic means as a large field of view repeating the, going back and looking again. So you may think that the sky is very static. You may as steady as the stars in the sky. Well, they are steady. They're more steady than us. But they do have, the stars do undergo changes. So for example, 4.5 billion years from now, the sun will cease. Okay, it'll become a white dwarf. Not a particularly spectacular anything. But for more massive stars, they'll undergo a supernova. Okay, the star actually explodes. And it's an important part of our life because if they didn't explode, there'd be no iron in your blood and you won't be here. Okay, and the reason you have a large amount of iron, if you look at the periodic table and say which fraction is large, its iron is because a lot of stars die. In fact, there's a star dying every second somewhere in the universe. So it's supernova, supernova, supernova. So there's stars dying all the time, okay? And our plan was very simple. Let's go and look for stars, things that change in the sky. So, some of this will be related to kind of business you folks do. And so what we have is we use this telescope for discovery. We've equipped this with a very large format CCD. In fact, if you want to ask who in the world makes the largest detectors, it's astronomers. We drive the detector field, okay? Then we verify that because we have real-time software which analyzes data, and then if it looks interesting, we observe the large telescope. Okay, how does a supernova, so here's a kind of a nearby supernova in a galaxy called Messier 51, or the Whirlpool galaxy. If you're an amateur astronomer, you'd know this quite well with binoculars or a low-resolution, low-power telescope, you can see it quite well. And there are two supernovae found recently in these things. And the supernova is marked here with these arrows. Okay, so here's our camera. It's a mosaic of CCDs. And it's 12 CCDs. These are very high-grade scientific CCDs. One of them is dead. We decided not to bother and just went ahead with these things. And just the moon has been photoshopped in just to show you the scale of what we can look at. Yeah, and the moon is about 0.5 degree in size. And this is real sky. This is all real data that you're looking at. So what do we do? Well, it's a large collaboration between various institutions, Caltech, Berkeley, Lawrence Berkeley Lab, Columbia, Oxford, Weizmann Institute in Israel, then Las Cumbres in Santa Barbara. And so when I put this together, I realized that in this sort of business, there's been a change in our field. In the past, you'd look at something like this and say, you know what, where is the capital cost? The capital cost is in making the telescope, the dome, the road, all this sort of stuff. Well, it turns out that's still true. There's still the capital cost. But if you look at a project like what we're doing here, the capital cost is actually a small fraction. So the capital cost needed to make this, buy the detectors, get a doer, install the electronics, refurbish the telescope, all that sort of stuff, get microwave links so we can ship that data to San Diego, all that sort of stuff is about $2 million. But the software cost is probably 5 times that. And I'm a very clever guy about this thing. So I called all these young people and I built the collaboration by saying, work for me for free, I'll make you rich and famous. And then after a minute I said, no, I'll only make you famous. Okay? So there are all these young guys. Josh Bloom is a professor at Berkeley. Jason Suresh, Peter Nugent works for DOE. Eran Ofek is now back in Israel. Robert Quimby is back to Japan now. Nick Law in Canada. So all these guys, they wrote a massive amount of software. The sort of software you write have to be, is sort of a thing that you really need passionate people, because if you really pay money, you don't have the money. So my rough estimate is the cost of our project about $10 million, of about 8 basically underwritten by all these people who work for free. Okay, so what happens in a data like this is every 60 seconds we get in this system 200 megabytes of data that gets off through wireless links, big microwave towers down to San Diego, then on to Internet 2, then on to Caltech and to Berkeley. And then the data analysis to start. So one of the first things we want to look for new supernova. So here's a new image, and here's the old image taken maybe a year ago. We subtract the two, and it's not as simple as, oh, well, A minus B, as what you might think. There are all sorts of subtleties, and takes about, this particular pipeline has taken about 20 man-years to develop. And when you subtract, you find something here, which your eye can't see as well, but the software pulls it out. But when you subtract these two, you'll also find something there. But then your eye says, you know what, there's something else here. That means it's a bad subtraction. So you can train people, and it becomes very boring. You can't just keep looking at this. So Josh Bloom wrote a lot of machine learning algorithms that actually understand what are real and things of that sort. And so all that stuff took a lot of effort. And that's why, as I said, there's a lot of software. And initially, we used to have crowdsourcing. And I never heard of this term about 2 years ago. And I now know what crowdsourcing is. Crowdsourcing is getting other people to work for you for free. Okay, so we put up all this data, and our Oxford colleagues developed a little software package that invites you, the citizen science, to come and help scientists. So you get tutorial, you go through some tests. Once you're done, they give you real data, and then you say, yes, it's a real supernova, it's not, and so on. And it's amazing to me to think that before every day, there's like 10,000 people around the world, doing stuff for us without even know who they are. They won't even be on a paper. Anyway, we now shifted from humans to robots because all of this has become robotic. The other sort of thing we have to do is reduce this data. Each of these stars, we make them into an entry in the table. And these are very large databases. In fact, one of the people in our group, he won a particular competition, and a supercomputing competition for large databases from this. So astronomers are very good at generating large data, but only after reading the New York Times to learn biologists are worse. They can generate even more data. Of course, our data are very high quality. Okay, so what have we done? So we have set up, basically, we converted this problem where astronomers go observe, find one at a time. We made this into an industrial machine. We discover supernovae not one a night. We're finding every 20 minutes. They're huge pipelines we run. They're actually very robust pipelines, because even if the data are bad, they have to recover. They have to continue processing. They have to make sure that it's a real supernova. They call up another telescope, all robotically. We have no one running these systems during the night. That entire stuff that's happening in Berkeley, Palomar, and Pasadena has no one at all, because we can't afford that. So in a short time, we have discovered 1,500 supernovae, and the global output till we began the project was 4,500. So in 2 years, we have beaten the entire world's output in 2 years. Not beaten, we have done a third. Okay, so this cartoon tells, so with that sort of a sample, there's lots of paper. We are writing a paper every few weeks now, you know. It's sort of a nice thing. You have this machine coming, you walk into the office, yeah, what's there today? And you find something interesting, you said, okay, why don't we bash off a paper? That's sort of my idea of doing science. And here's a cartoon which perhaps makes a little mockery of all these various types of novae and supernovae we find. Okay, so the next thing we wanted to do was low latency. So all this stuff was happening in our thing where we'd find a supernova and then there'd be a day's delay while we'd try to understand this. So we said, okay, let's decrease the latency in this pipeline. And as those of you write pipelines know, that's not so easy to decrease latency. Every factor of 2 to decrease in latency is exponentially harder. Anyway, we tried very hard. So here's an example about a year ago. PTF 10 VDL. PTF is Palomar Transit Factory. 10 means the year 2010. VDL is, we start with A, go through Z, then AA, and so on. So it's a simple thing. So we use a trick that you guys do. So we have collaborators in Israel. It's 10 hours away from us. So when it is nighttime in California, they're awake. So we said, okay, why don't you monitor the stream? So you can see here, the software figured it out a bit later. I don't know why. No, sorry, PTF, we got the data, the software figured it out and alerted, it alerts everyone. But then someone in Weizmann in Israel looked at it, they said, oh, this looks interesting because there's a judgment you have to do. And then right away, they deployed a telescope in the Negev desert. And then we said, oh, okay, this looked really interesting. We confirmed that this is not a statistical fluke. And then immediately we triggered a telescope in Chile, in Hawaii. This is a space telescope in orbit. In New Mexico, and so on, okay? So this was a tour de force, that we can all do this sort of sitting in a room, suddenly there's this armada of things you can do. And it paid off. It paid off. Just a few months ago, we discovered a very interesting 1A supernova. These are the supernovae that went into giving the glimpse of dark energy. That's a Nobel Prize. Some of my friends, in fact, received this year. So I'd ask you, where is the supernova? So I was giving this talk to a group of people, including a string theorist, and he said, well, you know, it's very easy. All supernovae come with an arrow. No, it's not true. They don't come with the arrow. We put the arrows later. Anyway, here's a supernova, okay? And we'll soon have a major press release in just about 10 days' time in Nature magazine, where we're publishing 2 papers. And this has turned out to, in like 30 years, this is the last one people found was 30 years, but they only found it 3 days later after it exploded. We found it 10 hours after it exploded. So we could do all sorts of tests and sort some mysteries. Okay. So in the same way, synoptic imaging at radio wavelengths. So hopefully I've given an idea that in this business, if you look at what it is, we used old telescopes. They're built in the 50s and 70s. The telescope cost has been completely depreciated, right? It's not a big cost. Yet, we are able to make something out of that. And the reason is because we are able to bring massive sensors and very high-speed computing, anything you can think of, all the things, storage, computing, transmission of data, sensors. We got all of them on, and that's why it's working very well. Now, the same thing is happening at radio wavelengths. Even though radio emission from outside the Earth was found by Carl Jansky, working for those days AT&T Bell Laboratories, the low frequency radio waves, like 300 megahertz, okay, wasn't very popular. It's undergoing a big renaissance right now. And the reason it's undergoing a renaissance is, in the past, if you wanted to do the radio processing, it was all analog. So if you wanted to introduce a delay, which is an essential part of processing, so here's a signal you get on a cable, and you want to introduce a delay, you actually added a long length of cable here. And if you wanted half the delay, then you had a little box which actually had a switch, this length, half length, quarter length, and so on. These days, delay, if you digitize a signal, you just change the index of origin. That's it, right? So the fact you have all these cell phones means that we can actually, astronomers can buy filters in this, radio frequency filters for 50 cents. Before we would make our own filters. So all the stuff that has made your life easy, unfortunately, when one part is making our life easy, which is it's allowing us tremendous decrease in unit cost, it's also adding problems because every time you guys talk on the phone or you use wireless transmission, it corrupts our signal. But nonetheless, that's how it is. So let me give an example of how this business is working. So the optical stuff was 10 years ahead. The radio is now just starting. So here's the largest telescope. It's a Parkes telescope in Australia, New South Wales. It built in the 60s. It still is the largest telescope, I think, in the southern hemisphere. And it was a pioneer in finding some things called pulsars, pulsating radio sources. Okay, now you'll be surprised that if you look over here very carefully, there's only one receiver. So it's as though I'm looking at the sky with one thing, you know. So if I want to make an image of this room, then I'll go, you know, raster scan and then slowly build up. Well, there are technical reasons. It was very hard to make those receivers. So 15 years ago, Australian friends, they built 13 receivers. And the reason it could happen is that many of these FET, the transistors, are actually very affordable now. In fact, at L-band, if you want to go all the satellite dishes, you can go buy for $50. When I was a grad student, which I admit was a long time ago, was a state-of-art thing. The performance is the same now. $50, you can go and buy that. Anyway, so they made this. So they had a 13 times multiplier. And they ended up finding pulsars in 5 years, which exceeded the entire global output. Okay, so that's a fantastic exponential case. So in Holland, they're building this low-frequency array. These are simple dipole things, slightly more sophisticated. But now you can take the data, the collected, and digitize it. And by current standards, these are not huge digitizations. Maybe you digitize at 200 megahertz. 200 megabytes a second. And it's fed to one of the largest computers in northern Holland. And they can make images of the sky on a daily basis, things that we couldn't have imagined 10 years ago. Okay, so the last topic I'll talk of is the lush submillimeter frontier. So what I talked before was like 100 megahertz. All that 100 megahertz is like a huge renaissance now. Now I'll talk about a terahertz, which is the submillimeter band. When I say submillimeter, I mean the wavelength, and when I say terahertz, it's the frequency. And I put this picture here because I think this subject is on for like easy science, and that's always my goal. The goal that I don't believe at all in working hard. I think it's much better to work smart. So always I really think for a long time before I do a project, maybe about three years or something, and then I want to do something where with the least amount of work, you get the maximum gain. Okay, because there are many ways you can spend time. Working hard is fine, but if you can leverage that, it's great. And the reason I put this is the field where I think it's going to be really easy. Okay, you can sit on the beach and write papers, and that's the kind of science I want to do. Okay, so let's look at why I think this is the case. So submillimeter astronomy, there are a lot of technical issues. The amplifiers you need to detect submillimeter or terahertz, they're not easy, okay? They're still state-of-art things. So some astronomer invented these germanium bolometers, and if you want to make these telescopes at submillimeter, so the telescopes need to have a finish of microns, few microns. So from one end to the other, you have to be perfect to in the same parabola at a few microns there. So it's a challenging mechanical engineering problem. So let's understand. So here they had this very small telescope, maybe a few meters across. And then, as I told you, that to make these amplifiers, the devices which take these radio waves and produce electrical currents out of that, there's a lot of noise in the way these things work at high frequency. So there's something called the NEP. We'll just not worry, it's 10 to the minus 14. The smaller that number, the better it is, okay? Let's remember, 10 to the minus 14 and a few meters. So what happened about 15 years ago is through a satellite called COBE, astronomers discovered that if you plot the universal spectrum, that is, if I could look at the entire electromagnetic spectrum of the universe, what would it look like? One is the wavelength axis, if you wish, or frequency on the top, they're equivalent. And then this is a number that's proportional to the strength. Most of the stuff, so 23 means in 23 units of something. The things we see with our eye is called the optical band, which is optical, near infrared, ultraviolet, all things thrown together actually, is 23 units. And 960 units is the 3-degree Kelvin background, which is the light that was given to us when the universe began. And then they discovered a whole new thing called the cosmic infrared background. So this really made study of 100 micron astronomy very popular, but that's a difficult band. So in an old style, the astronomers in the United Kingdom put this together. It's an in-house project. It costs more than 10 million pounds. Each of these bolometers were built by hand, very specialized things. Each of these horns were carved, and this is a very major project. It cost more than 10 million pounds, almost bankrupted UK astronomy in building this, and then they in fact found that this is an exciting field. But if you have to do things where each of them is so expensive and by hand, then you're not in exponential growth, you're linear. But it's changing, and that's why I think it's a lush field. So here's Moore's law at work, because anything to do with fab, foundries, Moore's law is always at work. So you can see that this is, in the last 20 years, you have a number of pixels in this. We started with 1 at the Caltech Submillimetre observatories, and then the new technologies that have come, that a colleague of mine has developed with superconducting detectors, and you can see there's a nice straight line in this log linear plot suggesting exponential growth. But that by itself is fine. If you really want the greatest accelerating returns, you need something else. And what's happening here is that NEP, the quality of these receivers or the amplifiers, is decreasing, and that's what it says here in log units. That means it's every 2 years they're getting better, because we understand the physics. That's the line here going down. Here, and this going down is better. So as a result of these two convergences, this is a field where if you can build a large, if you can just build a large camera, you'll be going from a few pixels to 10,000 pixels, all in a few years. And when that happens, the results come, obviously. So we are putting together a program at a telescope in the Atacama Desert in Chile. And for those of you who are James Bond fans, like I am, I think in Quantum of Solace, the big fight that happens in the end, it's in the Atacama Desert. It's not in Paraguay, whatever they claim. It is very close to where this telescope will be sited. It's a 25-meter submillimeter telescope. But the way to think of this, not as a telescope, like that's old-fashioned actually. The thing is, what we have is, we have a unique camera, which is maybe 10,000 to 100,000 pixels because of all this new progress we've made. Once we have a camera, I need a telescope. Oh, well, let's go build a telescope, okay? So the cost of this business will probably equal to the cost of the telescope. But that's when you actually get the greatest convergences. So anyway, I hope you are given an idea that astronomy is still romantic. You can go out and with or without good intentions with your girlfriend or boyfriend in the evening. But it's a field where, first of all, I want to tell you, it's an amazingly fertile field right now. It's not a coincidence that many things in astronomy are being recognized by various sorts of prizes, including the Infosys Prize. We have, one astronomer and one who works on things related to astronomy in string theory. And that some of this progress in our field is entirely driven by things that have nothing to do with astronomers. It's because things are happening elsewhere. So thank you very much. Okay, so the question is are the gamma ray bursts from center of Milky Way galaxy? No, I don't think we have. The chance of having a gamma ray burst in our own galaxy is probably once in a million years. And I don't think you really want to have one in our own galaxy. The question is the solar system moving towards the galactic equator? I don't think so. I have to think. I know we are obviously either moving away or we have a vertical motion. I think we are actually moving away from the galactic equator. Yeah. And I know there are some people who are thinking this is a cause of global warming as we come into extinction, but I think we are moving away.
I have a question. These days there are a lot of findings, even I think today's newspaper, about extragalactic planets.
Yes.
So what is the, can you describe what is the technology used and what kind of telescope you use for
Yeah, so the big progress that you read today is from a mission called Kepler. And I showed you, like, for our own facility, we had, you know, a mosaic of CCDs. Kepler carries a very large mosaic, 36 CCDs, frame transfer CCDs. And again, it wouldn't have been possible 10 years ago because the cost would have been, it would have been hard to make that many high quality CCDs. So Kepler carries 36 frame transfer CCDs, and it looks at a particular spot in the northern hemisphere, about 100 square degrees, continuously. And then it looks, if you have, let's say this is a star, and then there's a planet, and you are the observer. If a planet goes in front of the star, then the light from the star is diminished by the fraction of the size of the planet to the size of the star. And Kepler can make easily 1 part in 10,000 measurements, but it's even approaching to 1 part in a million measurements. And that's why you can start inferring planets through occultation.
Good morning. Thank you for the seminar, first of all. It was really interesting. I have a question. You mentioned that when a star dies, there are elements released and we can make use of them like iron and all. What is the process that goes behind it that releases the elements when the star dies?
Okay, good question. So the way stars shine in general, like the sun actually has a hydrogen fusion reactor in its center. Hydrogen is fused to make helium. So as the sun ages, the amount of helium in the center slowly increases. Okay, so for most of its lifetime, which is called main sequence life, the sun's energy comes from fusion of hydrogen to helium. Now, when the sun gets old, in the center, most of the hydrogen is gone, okay, right in the very center. You only have a helium core, and the sun is then not the energy supply drops. And when it drops, the sun can no longer keep itself puffed up. Because it's hot, it's puffed up. You turn off the heat because there's no fusion, it'll shrink. But once it shrinks, the density goes up, okay? And the nuclear, once the density goes up, it's high enough at some point, helium can start fusing with helium, okay? And then you produce carbon at that point. Then again, after a while, there's a lot of carbon, and it shrinks again. And then the carbon ignition takes place. Then but for the sun, probably it's not that massive. It forms carbon, and at that point, when it shrinks, even before the nuclear reactions that can take place, there's a new pressure called degeneracy pressure, which is purely of quantum mechanical origin. This was discovered by from Fermi, that if you take two fermions, electrons, and you confine them to a small volume, they don't like each other. Electrons really hate each other, so they get a lot of energy to be away from each other. So at that point, these electrons supply the pressure, and it stops. So sun becomes a carbon oxygen dwarf or something white dwarf. But if it is more massive than the sun, let's say 10 times more massive, then as it shrinks and the density goes up, before degeneracy can kick in, you can burn carbon into neon, magnesium, and then to silicon, and then finally to iron. There's something very special about iron. So as you fuse to higher Z elements or higher nuclear charge elements, you get energy. But iron is the most stable nucleus. If you try to fuse iron with iron, you get nothing. You lose energy. And at that point, the star loses all energy. So the reactions in chemistry terms becomes endothermic. That is, you need to supply energy to fuse iron, and the star has no energy to supply. So it undergoes a total collapse at that point. Okay, and why it explodes and so on, that's a much more delicate thing. But then the star explodes, there's all this iron. So the reason you have more iron is it is by nuclear physics. If you ask which is the most stable nucleus, if all the nuclei we know, iron is the most stable one.
Hi, good morning. There has been a lot of recent literature about 2012 being the year of increased or paranormal solar flares and solar activity, and it's sort of the impact on the Earth. So, is there really something astronomical about it, or is it just commercial fiction?
Well, the sun has an approximate cycle, okay, the 11-year cycle that's been noticed for a long time. But this is an approximate cycle. And somewhere in the 17th century, or is it 18th, I forget, it's called a Maunder minimum. For some, not 17th, maybe 400 years ago, I think. It's called the Maunder minimum. And the sun goes through its thing where it reverses the field. So it goes through quiet period, then active period, then quiet period, on an 11-year time scale. But about 400 years ago, the sun actually just became quiet. That means no spots were seen for almost about 100 years. And then there was a mini ice age in Europe, okay? So it's not impossible to think that the sun could be entering into a thing, which may be good news, is that if we don't attend to global warming, it's at least good to have help from the sun if it goes down a little bit. Okay, so we don't know. These are not so simply modelable. I mean, these are actually very tiny effects from an astronomer's point of view. Okay, we are very good at explaining the big effects, how the sun shines and so on. But the magnetic field and all, this only happens in the outer maybe a few thousand kilometers of the sun. And once your tiny effects, you really have to understand in great detail and understand the modeling. So I think, like many astronomers, we're in a wait and see period.
Another related question I had was, it was a bit of an anti-technology. A lot of, huge path-breaking discoveries in astronomy were at a period where, some of these technologies were just not there. For example, Indians were huge contributors to the field of astrology, and we didn't have any of these signs at that point of time. So, and the delta in the number of discoveries that we see is probably the magnitude of each of that is not to that extent. Probably, it's not the equivalent of a discovery of a hydrogen. We don't discover another element at this point of time. So what explains that, some of those huge discoveries which were made earlier and, not the discoveries that are happening now is not of that intensity?
Well, I think that is natural, right? I mean, let's say, on Earth, discover new continents. I mean, there are only so many continents. Once you discover that, it's very hard to do that sort of thing. So it's the standard analogy people give is our knowledge is like a sphere, right? I mean, as you increase, the sphere of knowledge, right? The stuff outside is still always bigger. But in terms of these basic things, it's very hard for me to imagine astronomers to come and tell you we discovered something totally new. Okay, I don't have any detailed explanation because it's not in that sense virgin new subject. We as I showed you in the second slide, 100 years, we really gone from amazing understanding, but there could be some interesting questions. So astronomers, for example, understand, I would say pretty confidently, what the universe was, let's say, being modest, maybe 10 to the minus 6 seconds after the Big Bang to now, we understand, I think. When I say we understand, I mean we roughly understand, okay? Good enough, we can actually connect to observations. Then the things before 10 to the minus 6, which I don't know, it seems very interesting. But then in astronomy we have, I don't know, the discovery of dark matter and dark energy. I would say it's a huge discovery. I don't know whether you're aware of this, but the universe has something called dark matter, matter which doesn't interact with other matter. It therefore cannot make any energy source. And there's dark energy. There's some in this room. Every cubic meter has 1 electron volt of, 1 GeV of, 1 GeV. I think it's 1 electron volt of energy. We don't know that, and it was only found 20 years ago, or in the last 20 years. So to think that we have been, it's sort of like a strange thing. We are living in this universe where the people we see and understand, sun and all, is 4%, and the 96% we know nothing. So I think that's not a bad discovery. And that's what the Nobel Prize this year has been given, is to tell that 70% of the energy in the universe is unknown. We know it exists, but we don't know what it is.
Professor, good day. My question was actually partially answered by your answer right now. I wanted to know what are the latest developments on dark matter and dark energy detection which is happening, And with regard to quasars, at what stage of understanding them are we at this point? I understand from the latest papers that we're still quite far away from understanding them. And the final one was supermassive black holes and how they tend to balance out the whole sort of cosmic equation where, creation, destruction, and all. So I just wanted to know your viewpoints and where are we on these at this point?
Yeah, for dark energy, I have nothing to add. I mean, I think the proof that there is something called dark energy, which causes expansion, is there. And dark matter, I'm more optimistic. I think we will probably, someone will discover these, eventually they will see evidence of these particles in some sort of a laboratory experiment, some underground experiment perhaps. And that would be fascinating to know, what 30% of the, or all the matter, of which we only know we are like the dregs, to actually discover what is true matter, I think would be pretty amazing. Supermassive black holes, I'll put in the category, yeah, they're interesting, it's like this, there's a lot of cannibalism in the universe, as just showed you in that simulation. There are galaxies colliding with each other, ripping off stars and so on. So the only interest, so if these massive black holes are a result of simple cannibalism, it's okay, it's a phenomena. But if some of these really are formed when the universe began, very early on as seeds, well, then I would say that would be very, very interesting. The jury is out though. I'm not an expert, so I can't tell you, other than if we can show that some of the supermassive black holes, their seeds began very early, then I would say there's some basic physics we really need to understand.
Professor, this is Ramesh. What is your view on the recent about this something moving faster than light?
Yeah, I have no opinion really, because it's a tough experiment. The way the faster than light experiment was done is it's an underground mine in Italy, and they're looking at neutrinos coming from the collider in Geneva. Okay, so one is a surface source, the other one is underground. So really, it's a question of you have to understand the exact distance between where the neutrinos are generated and where they were detected. Okay. Now, if it is on the surface, we could use GPS, we could do this, and so on and so forth. Now, so if you have to go a few miles below, okay, then you have to reference the detection to the surface and from the surface to Geneva through GPS. Okay. So many people saying, okay, maybe it's only in the end, it turns out to be something like 30 centimeters, I think. And that's a bit hard to immediately say, yeah, I mean, these guys are good guys, they've done their best, but 30 centimeters from, it's not like a simple tunnel, it's some sort of a thing that we go back and forth. I mean, they must have done, and hopefully it's not some string they started from there and gone to the top or something. But usually great results in anything require great proof, and I don't think it is at that level.
You said there was a homogeneous soup out of which the gas pockets were formed, and then they contracted, galaxies have been formed. But then Big Bang theory says something different, right? Like I mean, everything was in a single point and then it exploded and then galaxies have formed.
The Big Bang theory doesn't say everything was in a single point. That's a common mistake. It was not an explosion. An explosion is a single point. If I have a bomb, it explodes only here, not there, right? So the way to look at the Big Bang theory is there's an explosion at every point in the universe, okay? Because the universe is, there's no special location. So very hard to imagine that, okay? To have, so whatever you see here should be the same as seeing there. Therefore, everyone should see the explosion, okay? So, and so yeah, there was a very uniform soup. Now, if the universe was perfectly uniform, completely uniform, not even to 1 part in a million, but 1 part in a trillion or whatever, you and I won't be here. The fact is that slight uniformities, non-uniformities, which are a result of quantum fluctuations, which we can measure but may not fully understand, that non-uniformity, so there's let's say 1 part in a million more here and somewhere less, then this has more attraction. It'll attract matter. And over a long enough time, it attracts enough matter to build galaxies.
Also, I have a question. It's outside of this presentation. Actually, my question is, recently I started reading few books by Richard Feynman, and he seems to be an interesting guy. So since you also worked in the same place, did you have an opportunity to interact with him? And if so, could you please share some interesting facts?
Yeah, I had a chance to interact with him when he was alive. He's now, as you know, dead. No, but it's not like I went to Dick Feynman and say, yeah, okay, why don't we sit down and chat and so on. It was a great personality. The only thing I would do is when I was a young faculty or a postdoc actually for a year, he had a parking spot, and parking spots in Caltech are valid till 5 p.m. And every day in the evening when I came out to park in his spot and tell my mother, you know what, Richard and I share the same parking spot. Okay.
So my question is about antimatter. So there were some experiments conducted in 1930s, I guess, for the manifestation of that physical existence of antimatter particles. So are there any foolproof? I'm not sure about that. Whether, are there any manifestation or experiments regarding the anti-universe thing? For any completely, for all the particles, there is a different anti-particle for that. So.
Yeah, so the question is, why does the universe have matter and antimatter? Okay, because we believe there's no antimatter left in a big way. Okay, there are many reasons now that other than if we say there's another universe, it's made of antimatter. Okay, I can't, that sort of gets into a hypothesis-only model. But I'm saying if there was really, as the simulation showed, the gas is mixed up a lot. So if there's any pocket of antimatter of any sizable things, it would interact, it would produce large number of gamma rays, and which you would see in the gamma ray background. So we believe the universe is largely matter. In fact, almost purely matter. Okay, but that's one of the great mysteries of life, right? That matter and antimatter are exactly equal, but when the universe began, nature had to choose one or the other, because the simplest option would be equal amount of matter and antimatter, then it'd be done. Then nothing would happen because they'd collide and it would be pure photons and the universe would go on. So something chose what we call as matter. You could call it antimatter if you want, then the other one will become matter. Something chose one species over the other. Okay, and that's an example of symmetry breaking in physics. And usually when that happens, there's an underlying very deep physics.
At the starting, you mentioned that astronomy is an expensive science. In fact, some of the projects you have shown involves huge amount of money to the sum of billions of dollars. So how can you say it is justified when the world is facing this economic downturn? US itself is in some trillions of dollars of debt, and to the people like us, it doesn't seem to contribute directly to the society.
Yeah, that's true. But you could ask, the question is, what is the role of pure science even when we have money? Okay, because the question of money, so there are many ways I could ask. The US DoD budget recently released $660 billion. Now this is the known part of the budget, right? So it's not like the country doesn't have money. It's a question of how you want to spend money. So I don't think this question can always be asked independent of the economic circumstances of any country. And it can be asked in a country like India, okay, we have bad roads, 40% of the population probably receives only one meal a day or less. So why should you do astronomy? And I would say if with that particular perspective, it would be very difficult to answer other than for some reason historically, if you look traditionally, regardless of what the kind of governance has been, whether it's a king or whether it's a dictator or it's a democrat, etc., people like to imagine something a bit beyond themselves. There's a certain feeling of life other than themselves, and so it expresses, and some people call it as culture. Why should we have music? What does it really? Does it contribute to economic activity? Or worse still, cricket, which I think contributes negatively to any economic activity. So when people ask that question, I'll say, what does cricket mean? Why do people sit around and watch some athletic guy chasing a ball? I mean, where is the culture here, right? So I think these things like arts and sciences actually serve as a deeper sense of who we are more than anything else. And if then I can give you the more straightforward argument. Something like astronomy has actually contributed. The reason astronomy is so well supported in the US and will be supported is we have contributed tremendously to the economic as well as the defense well-being. If you go to many large defense establishments, you'll find them will be populated by a third of astronomers because astronomers are very well trained in fluid mechanics and explosions. So a lot of the basic equations of nuclear explosions, the fluid part comes from astronomers. In terms of sensors, we drive the sensor field, okay? Near-infrared detectors, we drive all those things. But I regard that as a weaker answer. It's like saying, let's fund to do X and Y. So yeah, I would say there will be no limit, and I think each society should decide. And roughly, I would say this is a cultural question. And in fact, to me, as I said, the other thing that I don't understand is really spectator sports, its value is so low and its legacy value is negative, I would say. And yet, I'm sure many in this room watch cricket. They probably spend a lot of money in that stuff. I would say, why do you do that? So I don't think there's a simple answer other than I would say my most arrogant answer is I think that's what cultured people do. Okay, since you've been patient, so I thought, this is, some of it maybe is, so hopefully, first of all, you understood there's a lot of software stuff we do. It's perhaps very different from what you do. But I thought, you guys have spent a good hour and 25 minutes. I'm sure that's the last loss of productivity for the company. So let me help the company back, or at least help you guys back. So with some practical knowledge. So next time you go to Australia, one thing is you have to understand, I have many Australian friends. I was just in Australia a week ago. It's a nice country, and it's a very small number of people, 20 million, big continent. And therefore, they're a bit, let's say, gullible. Okay, that's my general opinion. So here's what you could do to compensate your hour and a half of loss of productivity. You land in Australia and you catch hold of an Australian person and say, look, I know a lot about astronomy. Show me a $50 bill, and that person will show you a $50 bill. And then you say, okay, the lights are a bit dark. Otherwise, if you could dim that, that's the Parkes radio telescope, the one I showed. Okay. And over here is the pulsar signal. It's a real pulsar tracing. And the Australians are very proud of their radio telescope because it was a large telescope built in the 60s. So, you should, at this point, have learned enough jargon from this talk, this and that. That's why you have to do a bit of work. And if you do a good job, you can pocket the $50 bill and you'd be a little bit ahead. Okay, thank you very much.